This conference will now be recorded.
So, very good evening, Deepa. We'll learn today about nuclear size, nuclear density, then mass defect, binding energy, and we'll discuss the binding energy curve. If time permits, we'll discuss about nuclear forces. So, let us start our class. So, see, nuclear size we had seen in alpha particle scattering experiment. The size of the nucleus is very, very tiny, and it is of the order of femtometer. It is of the order of femtometer. Femtometer means 10 to the power minus 15 meter. So this is nearly the size of the nucleus. So this is uh, we have seen this can be estimated by scattering experiment. And see, nucleus is not like an atom. Atom is a solid, okay, but nucleus is not like an atom. It is not a solid object, and it does not have well defined boundary. So this is one important point. This does not have well defined boundary. So that's why what we do, we estimate the size of nucleus by scattering experiment. And from scattering experiment we know distance of closest approach. We have discussed in the atom chapter distance of closest approach. Okay, so this is the distance of closest approach is the estimated size of the nucleus. Okay, so for various nucleus, this size of the, like for various element, size of the nucleus has been estimated by scattering experiments. Like say in this case alpha particle was used to bombard the nucleus or atoms, gold foils, and various cases like neutron sometime, high energy neutron, then maybe some cases proton. Okay, and some cases electrons also have been used for scattering experiments for various elements. And calculating this closest approach, okay, most of the cases we can find out or estimate the size of the nucleus. And see, we can think of the shape of the nucleus to be spherical in ideal cases. So maybe it is spherical in shape. Spherical in shape, we have already learned in the 11th standard what is sphere, etc. It has three coordinates. Okay, so spherical in shape. And from various results like experimental results in the we can see that the size of the nucleus or the volume of the nucleus is directly proportional to its mass number. So this actually this particular fact is being known from the analysis of the experimental results. So what is say? It said the volume of the nucleus is directly proportional to its mass number. If I write, so nuclear volume is directly proportional to mass number. Now look, ideally we can take the nucleus in spherical shape. Then if r be the radius of a nucleus, then see we can write this volume as this proportional to a, right? So this is what we can get from experimental result. See what does this mean? If I write once again, 4 by 3 r cube is directly proportional to a. This means, if I write what is the, so this directly proportional to a, and r is directly proportional to cubed root of a. Okay, so this is the formula. So radius of any nucleus is directly proportional to the cubed root of mass number. Okay, this is very, very important, and in various numerical, like various competitive exams, and also in the board exam, you may get a question from this nuclear size or nucleus radius. So this is called nuclear radius. If I write in terms of equation, we write this. Okay, so this is the proportionality constant. Okay, and it has a value, constant value, nearly 1.2 into 10 to the power minus 15 meter. That means 1.2 femtometer. Okay, fm, femtometer, 1.2 femtometer. So now see, if we have various elements, like say if I take aluminum for suppose, like say aluminum has a mass number. So for aluminum, what is the mass number? That is 27. Okay, for aluminum A is 27. So if this is given in the exam, you might be asked to find out what is the radius, probable radius of aluminum nucleus. So you can calculate easily using this equation. Look, this one. So I can write R is equal to, for aluminum, this is R0, that means 1.2 femtometer into the 27 cube root of 27. So this will give you 3. So you'll get 3.6 femtometer. Okay, so this will be the size of the nucleus of element aluminum. So like that you can find out for various elements. And sometime you might be asked to find out the, or compare the, we can compare the size of the nucleus or radius of the nucleus for various elements with this formula. Okay, so this is the nuclear radius. Okay, so we have seen nuclear radius, r is equal to r0 into cubed root of mass number. Okay, I'll just write it here, cleaning everything. Let me write it here. R is equal to r0 a to the power 130. See, this is actually mass number of particular nucleus. What is mass number? Mass number means number of proton plus number of neutron. Okay, this is the one. Okay, anyway, now look, if you know the radius, can you find out what is nuclear density? So how do we define density generally? So this, right, rho n, that means nuclear density. So density is actually mass. Okay, mass over volume. So mass of nucleus, suppose mass of nucleus. Okay, mass of nucleus, and suppose this is the volume of nucleus, of nucleus. Okay, so in this case, look, if I say that Okay, let us uh, take one example. Okay, so if suppose small m is the mass of each each nucleon. We have discussed what is nucleon in the previous class. Nucleon, I'll tell you once again here what is nucleon. So nucleon means the proton and neutron together are called nucleons. Okay, so let us say this small m is the mass of each nucleon. Okay, mass of each nucleon. So if the a is the mass number of the nucleus, then what is the total mass of the nucleus? See, mass of the nucleus, I denote it with capital M, so it will be small m into a. So this is the total mass. Okay, now see, how do we calculate the volume of the nucleus? Volume of the nucleus. So this is volume. We already know 4 by 3 pi r cube, right? So this r cube we can just replace with this part. Okay, we can replace the r cube with r0 into r0 into a to the power 1/3 whole to the power 3. So this gives you 4 by 3 pi r0 whole cube. This is a. I hope it is clear to you. So this is the volume. So what we have got? We have got the mass of the total mass of the nucleus. We have total volume of the nucleus. Now let us write it here. Okay. So let us write it here. So what is the total mass of the nucleus? Small m into capital A. Okay. And what is the volume? Okay. This is the volume, right? So look here. This density. See this A. They both are mass number. So I can strike them out from numerator and denominator. And look, this particular term is actually a constant term. Okay, this is a constant term for a particular nucleus. Okay, this is actually constant, not even particular. For each nucleus, this is a constant term. So you can see this is constant. So what does this mean? This mean, see, I'll write it here. What does this mean? Let me write it here. What does this mean? So nuclear radius. What does this mean? Nuclear density. Nuclear density is independent of a. That means what? That is size of the nucleus of nucleus. That means what? Nuclear density is same for all the elements. It does not depend on the mass number, neither it depends on the size or the radius. Okay, since it is independent of a, so it does not depend on mass number, or in other words, it does not depend on the size. So nuclear density is more or less same for all the elements. So this is the important concept you should know, that the nuclear density is independent of mass number or the size of the nucleus, size of nucleus. Okay, so this is the corollary from here. Now let us see this. These are the points I have written it down here. So we have seen that the nuclear density, which is m by v, was given by mass of each nucleon by 4 by 3 pi r naught cube, which is a constant term. Okay, so nuclear density of okay, so uh, all the elements, nuclear density of all the elements is the same. And then see, nuclear density for matter is of the order, see, of the order of 10 to the power 17 kg per meter cube. So this is huge. This is a huge density. This value is really a huge number. And you know, this kind of density you will be able to see in neutron stars. Okay, neutron stars, etc. So in these cases, you know, temperature will be very high in the inside the neutron stars. The temperature is very high. Okay, nuclear density is not uniform throughout the nucleus. Another point is that if you have a nucleus like this, so density maybe it may be possible that density is rho 1 here and rho 2 here. So you know, so density is not uniform. That is what it is said here. So density is not uniform in case of nucleus. Okay, so these are few points you should remember for the density of neutron. Okay, so we have learned what is nuclear size, we have learned what is nuclear density, how it depends on the mass number and all those things. Now what we'll do, we'll discuss one important topic today, that is mass defect, mass energy equivalence and nuclear binding energy. Okay, so let us see first what is mass defect. You know, you might have a nucleus. Suppose if you take, for example, if you take some nucleus like helium or anything else you take. So helium, let us take helium 2He4. So this is a compact like nucleus, and it has, see, neutron. I'll write number of neutron by small n and number of protons by small p. So it has 2 proton and 2 neutron. That's how the mass number is 4. Okay, all right. So it is seen that the mass of, let me write the masses of this corresponding neutron, and see, let me write. So mass of neutron, free neutron is Mn, mass of free neutron, mass of free neutron. Okay, and Mp, mass of free proton. And let me take capital mass as the mass of the nucleus. Okay, nucleus. So it is seen that when 2 neutron and 2 proton in combination make this helium nucleus. So this is the mass of the helium nucleus, and this mass is actually, the mass of the helium nucleus is less than the total mass of the constituent neutron and proton. You might be having little difficulty to understand here. If I write it here, you will be able to understand. Suppose the mass of the, see, according to, if I go with this way, like free electrons, say free neutron and free proton, they have masses. So if I multiply 2 into Mn, because there are 2 neutron in the helium nucleus, plus 2 into Mp, this mass is actually greater than the mass of the stable helium nucleus. Stable helium nucleus. Okay, so this is what is called the mass defect. If you take the difference between these two masses, then you will get some surplus masses or extra masses for this you have. So that is called mass defect. You look here, the difference between the rest mass of a nucleus. So rest mass means what? When a nucleus is at rest, that is called, and at that configuration, when it is at rest, the mass of the nucleus is called rest mass energy. When obviously you see in the higher classes you will be learning special theory of relativity. There you will be able to understand again the difference between the rest mass and and the mass of an object when it is in motion. So special theory of relativity will tell you in great detail in the later like higher classes. Relativity. Okay, STR. It is called STR in short. So this says that any object which is in motion, obviously not only like few kilometers, it has to be like as like nearly as the speed of light. If the v is nearly equal to c, speed of light in the vacuum, then the mass of that particular object in motion will not be like that will no longer be rest mass energy. So rest mass energy, see that mass energy, that mass will be actually called relative mass, and that will be obtained by 1 minus c m0 divided by under root v square, under root 1 minus v square by c square. So this will be the relativistic mass in case the object is moving with very great speed, which is comparable to the speed of light. So then that object will no longer possess the same mass as rest mass. So that mass will be relativistic mass. In fact, this factor is less than 1. So the mass will be increased. Okay. So all right. So what I'm trying to say is that a stable, see the difference between the rest mass of a nucleus, that means see here in this case helium nucleus. Okay, let me now take a specific example, writing the composition of the nucleus Z, and this is A. Okay, so you know here you have number of neutron. Let me write number of proton P. Number of proton P is Z. Number of neutron will be A minus Z. Okay, so as I said, let mass of the neutron be denoted by Np, and this mass of the proton is denoted by Mp. Then according to our definition of the rest mass, mass defect, what I can write, this is the difference between the rest mass of the nucleus and the sum of the rest masses of its constituent nucleons is called mass defect. So according to this definition, so mass defect is always written as delta M, and look what it will be. It will be n into Mn, as we had written n into Mn. Sorry, this is the mass of total neutron present in the nucleus plus mass of the proton present in the nucleus, and this mass of mass of the nucleus itself. Okay, if we write like this, look in this case, n n is actually, I'll write that later. mp plus, see, n is a minus z, a minus z mn. So this is here p into mp, and this is a minus z into mn minus. So this is always greater, so you have to take the difference. So if you see, so this is how we'll write the mass this is how we'll write the mass defect. So this is how we'll write the mass defect. So p is z here, p is z. So p is z, z into mp plus a minus z into mn minus, like, whole, this you just add them up and then subtract the mass of the nucleus, then what you get is called mass defect. This is called mass defect. Mass defect. So this happens for each and every nucleus, that any nucleus, stable nucleus, has lesser mass than the sum of the rest masses of its constituent elements. Okay, constituent nucleons. Okay, so I'll write it here, mass defect delta m is equal to zmp plus a minus z mn, then m, mass of the nucleus. Okay, so this is the mass defect. Now you look, mass defect. Now this is where this mass energy equivalence comes in. So what is mass defect? We have learned, and see, Einstein gave mass energy equivalence by an equation. See, that is E is equal to m into c square. This, even non-physicist people also know this, like, who has never read physics also, they know E is equal to mc square. Okay, nowadays. All right, very nice. So what does this mean? This means actually this, see, energy and mass, they have direct correspondence. If suppose m amount of mass is destroyed, it will produce, or if this much amount of mass disappears, then m into c square equivalent energy will be released, okay, or manifested. So this is the like, this is what mass energy equivalence equation says. Okay, yeah, so that's how, according to Einstein, or according to special theory relativity, we should not have separate mass conservation law of mass, or conservation law of energy. So we should have combined conservation law of conservation of mass and energy, law of conservation of mass and energy. That means in any reaction, nuclear reaction or any reaction, the total mass and the total energy remains the same. Okay, this is what was EMC square. So E is equal to MC square. This is mass energy equivalence, equation of mass energy equivalence. Now you might be thinking, sir, why do we need to know this mass energy equivalence formula? Yes, we need to know this because, see, this mass defect we have got. Defect means, see, if I have two, as I have given an example, 2He4. So it has two proton and two neutron. Two proton and two neutron. So if I somehow able to take two proton and two neutron together and to make a nucleus, then this people have greater mass actually. They have greater mass than the original nucleus, helium nucleus. So this excess mass, how does that disappear? Actually, that does not disappear, it converts into energy. So this defect, this is called mass defect, and the equivalent amount of this mass defect, there is an energy called delta m into c square. This equivalent energy is converted to binding energy of the nucleus. Okay, I hope you have understood what is binding energy. So what is binding energy? You have neutron, proton, neutron, proton in a very close spacing, like see spacing between nucleons is somewhat like this. So this is very very tiny distance among each other. So this defect of the masses, gets converted into energy that is called binding energy, which holds all of them together in a compact space, in a very very tiny space like 10 to the power minus 15 meter. Okay, so this is what actually binding energy. I hope you have understood what is the what is the binding energy. Binding energy will just define here. What is binding energy then? Binding energy of a nucleus may be defined as the energy required to break up a nucleus into its constituent and protons and neutron, to separate them to such a large distance that they may not interact each other. So that particular energy is called binding energy. So we have seen that you have seen that there was mass defect if we just take the masses of only constituent proton and neutron, then the mass was greater than the original stable nucleus. Okay, so if you just take a difference, that is called mass defect, we have seen that, and see this mass defect will manifest as binding energy. That means you have nucleons, so they will be actually bound strongly to each other. Okay, so that energy, that energy actually is called binding energy, and mass defect is the origin of this binding energy. Mass defect. So mass defect is the origin of the binding energy, which holds or which binds the nucleons very tightly in a very compact spaces, okay, or very tiny spaces. Okay, so if we want to break, suppose I was giving an example. Suppose I have this nucleus. If I want to break this nucleus into its constituent proton and neutron, suppose z protons I have to get, and a minus z. If I break this nucleus to get a minus z number of neutron and z number of protons, then to break this nucleus we need to supply energy. We have to supply energy. Why? Because we have seen that mass defect into c square, this much of energy is actually holding the neutron proton together in a very very tiny space. This is called binding energy, and this is how we will be actually calculating binding energy, mass defect into c square. Okay, so what is binding energy? The energy which is required to break a nucleus into its constituent elements and to separate them out from each other such a long distance or large distance so that they may not interact each other further. Okay, so that is called actually binding energy. Now what is binding energy per nucleon? So okay, before I go there, let me tell you as a definition how do we write the binding energy. So how to write binding energy as a definition? So I have already told you what is mass defect. So mass defect, so binding energy sometime it is written as B dot E, or sometime binding energy B dot E dot, or sometime binding energy will be denoted by E capital B. Okay, binding energy. So this binding energy is mass defect into C square. So what was the mass defect for that particular nucleus? So it was Z into MP plus A minus Z into Mn. Okay, this minus minus mass of the nucleus, mass of the nucleus, let me write as Mn. Okay, mass of the nucleus. Okay, this is the delta M. Now what is Eb? Eb will be, binding energy will be Z mp into A minus Z Mn minus Mn. Okay, so this bracket has been given wrongly here. I can put some other bracket. Let me give curly bracket here and then whole bracket over here into C square. Okay, this is the binding energy. Now this is binding energy. What is binding energy per nucleon? I'll write it here. What is binding energy per nucleon? So binding energy per nucleon is given by binding energy divided by mass number. What is the mass number? Mass number is the total number of nucleons. A is Z plus A minus Z, right? See, this is the proton, this is the neutron, so this gives you mass number, right? So mass number, binding energy per nucleon, binding energy per nucleon is given by binding energy divided by mass number. Binding energy divided by mass number is called binding energy per nucleon. Now, one good thing is that if we draw this mass number, see binding energy per nucleon for, okay, so binding energy per nucleon is actually called, okay, so I have just left one point here in the mass defect. Mass defect per nucleon is called packing fraction. Okay, mass defect per nucleon is called, mass defect per nucleon is called packing fraction. Okay, mass defect per nucleon is called packing fraction. And now mass defect, sorry, binding energy per nucleon, binding energy per nucleon, binding energy per nucleon is called, like is defined as EB by mass number. Binding energy per nucleon is called binding energy by divided by mass number. So if we write it here, the same thing, Z mp divided by A. So this will give you binding energy per nucleon. Okay. Now if we plot the binding energy per nucleon with mass number, then this peculiar curve you will be able to get. Now we have to understand what does this curve mean and what are the values of various values of various nucleus meaning here. Okay, okay, let us find out few characteristic features of this carb. Look here, carb starts from, so in the x-axis it is mass number, and in the y-axis it is EB per mass number, that is binding energy per nucleon. And see, binding energy is actually having a very large value, very high value, that is in the order of million electron volt or mega electron volt. Okay. Now in the y-axis it is binding energy per nucleon, and here it is the mass number or the total nucleons. If we plot this particular value for each of the element, and then we plot, you look, this is the deuterium, tritium, then this is lithium, this is nitrogen, this is helium, this is carbon, this is oxygen 16, this is oxygen 18. So you look here, when we start from 2 to 20 mass number, around here, this is 20, yeah, so around this place you can see there are ups and downs, that means peak and dip, peak and dip, peak and dip. So this part is not very smooth, otherwise the curve is smooth. Okay, so this is what we can see. So we see here the binding energy per nucleon is actually popping up or having a value, see, which is showing a peak kind of thing. Here is helium, and say carbon 12 and oxygen 16, they are having like greater binding energy than lithium, nitrogen and oxygen 18. So you can see. So what does this mean actually? This means that this helium, this carbon 16, sorry, carbon 12 and then oxygen 16, these are much more stable than this lithium, nitrogen and oxygen 18. Okay, so this is what it is actually. Yeah, so up to here this curve indicates that the lithium, then nitrogen 14 and oxygen 18, so these are having lowest, like they are having lower values of binding energy with respect to their neighbor, like say helium for lithium, and then carbon for this so carbon has greater energy than binding energy than this nitrogen. Again oxygen 16 has greater energy than oxygen 18. So this means that compared to lithium, helium is more stable nucleus. Again, compared to nitrogen, the carbon 12 is more stable nucleus, and oxygen 18 is less stable than oxygen 16. So the binding energy per nucleon is plotted with mass number, and we can see this kind of characteristics like in the, for the light elements like deuterium and tritium, then protium, for them the binding energy is very less. That means those nucleus like protium, this is deuterium, this is tritium, these are actually not very stable, not very stable element. Okay, because their binding energy is very less. Now if we look the mass number around 32, like if we look the mass number in between 30 170, this range almost from here, you can see from here 32, so 30 means here, from here almost, so here from here to here for all mass number the curve is more or less stable actually, 120 up to here. So they see this curve is almost constant. Okay, almost constant, almost constant, and this has a value of around 8.5 MeV, this constant value. Okay, This constant value is how much? 8.5 MeV per nucleon. You can see from here. So and beyond, see mass number beyond 170, actually this for those nuclei, see the mass number actually decreases. See from here, mass number decreases and it reaches to a value of something like 7.25 or 7.5, something like that. Okay, it reaches to a 7.6, 7.6, almost 7.6 value. Seven point six, almost this value is 7.6. For heavier nuclei, you can see this is tungsten, this is uranium. Uranium has the least value of binding energy. So what does this mean? We have seen that the binding energy means the energy which is required to break away the constituent neutron and proton. So for those nucleus, like those nucleus for which the binding energy is high or large in this region, see the average binding energy will be something like 8.5 MeV. In this range, the nuclei are more stable, more stable than nuclei having a greater than 170. Why? Because see, when this mass number is increasing, that means neutron and number of proton also increases. Number of protons also increases, and since proton there is a repulsive force, electrostatic repulsion. So when the number of protons becomes very large, that nucleus becomes unstable. They become radioactive. That means they spontaneously disintegrate. They will disintegrate, and we can see that the maximum binding energy is for iron, and that is actually, see, I'll write it here, EB for iron is the highest or the maximum. It has a value something like 8.8 MeV. Nearly this much value is there for iron. So that's why iron is very stable nucleus. It is not a radioactive nucleus. Okay. So these are the characteristic features of this binding energy per nucleon carb with mass number. So you have to learn this curve and understand each and every point. See why these spikes ups and down, because these are less stable than this. Okay, this is what it mean by that binding energy spiking. Okay, or the curve is not smooth over here. So so the nuclei, see, like protium, then deuterium, then tritium. These nuclei are very light, even helium, etc. They're very light element. For them, the binding energy is very less. That means they are very less stable. So that's what we can infer from the curve. Now look, we'll see what are the importance or what are the physical significance we get from various values of binding energy in this, or what we like what uses we can have, or how we can use various elements in this curve to get energy for our day-to-day life. Okay, look, the importance of binding energy per nucleon curve, nucleon versus mass number curve are the following. So from this curve we can explain the origin of fission, like the origin of the energy released in fission reaction and fusion reaction of nucleus. Okay, so from this curve itself we can guess or we can understand that how huge energy is being released in the fission reaction. So this fission and fusion reaction we will be learning in the later classes, and the energy released in those reactions is due to uh, this binding energy, the value of binding energy. You can see when a heavier nucleus. So we have seen that for nucleus, like nucleus having mass number greater than 170. So we have like very famous very famous nucleus 238 uranium, that is actually that is radioactive nuclei. They, because of this very large or very high mass number, it spontaneously disintegrates into some other daughter nucleus. Sometime it will give you krypton, sometime barium, kind of those things. Okay, all right. So what I'm trying to conclude here is that when a heavier nucleus splits into two lighter nuclei, the binding energy of the nucleon changes from very low value to some value, average value. So greater binding energy of the product nuclei result in liberation of energy. So I'll just repeat this thing, that the binding energy per nucleon is smaller for heavier nuclei that we have seen, that is 7.5 or 7.6 for 6 for nuclei greater than 170. So for heavier nuclei, this nuclear binding energy per nucleon is very small. But for the middle ones, they have heavier nuclei. Okay, so they have they have actually large binding energy. So that's how they are more stable in the middle portion, like 32 mass number 32 170. Okay, if I just mark it here in between them, 30 is yeah. So something like here. From here, see the mass number is almost constant up to here. We can take. Okay, so these are most stable nucleus, Okay, and these are having less binding energy than at least this portion. So this they have 7.6 MeV, and here it is 8.8 MeV. Okay, so this, so when we take very large nucleus like uranium 230, and it is actually it breaks into two daughter nuclei like krypton, barium, or whatever. So then those daughter nuclei have the greater binding energy than this uranium itself. You know why? Because the earlier the nucleus was having this much mass. Now for the lighter nuclei, you need how much? You need very light element, like say you have 156 or something like 90 or whatever. So you have this to let me just do one thing. Let me take, this is barium 156, I know. This is krypton, so 238 minus 156, that means you get 2 8, so 83. So 82 or 83, another element has 83 suppose, or 82 mass number, sorry, yes, mass number. So these smaller masses, actually because of losing masses only, they have been like this. So lost in mass actually gets converted into binding energy, and that binding energy, so this will have actually greater binding energy, like almost some 4.5 or 4.4. So these two daughter nuclei have greater binding energy. See, this greater binding energy of the product nuclei results in the liberation of energy, and this is the basic principle or basic uh, rule, sorry, not rule, I should say basic understanding of fission reaction, why this much amount of energy we get from nuclear fission reaction. Because of this, when a heavier nuclei split into two lighter nuclei will be having greater binding energy, and this greater binding energy is the origin of liberation of energy during fission reaction. Now let us go to the fusion reaction. See, in the fusion reaction you have to look for this particular portion. So when you have, I'll clean everything. So when you have lighter nuclei, they have very less binding energy, so they are also very less stable. But now if you take two lighter nuclei and then fuse them to make a heavier nuclei, then in that case also you get greater binding energy. Okay, maybe on an average this it goes from where, it goes from 7.6 MeV to this much. So this, in this case also, in fusion also, when two light nuclei combine to form a heavier nucleus, the daughter nucleus has greater binding energy. The higher binding energy per nucleon of the product results in release of energy, and this is actually the principle of hydrogen bomb. Principle of H bomb, hydrogen hydrogen bomb. Okay, fusion reaction event. See, sunlight or sun energy from the sun we get, that is actually produced by fusion reaction. Sun energy. Okay, so fusion reaction. Okay, anyway, so with this I'll stop it here. We'll discuss the nuclear force because it is also a very good and important topic. We'll discuss in the next class about nuclear force, and also we'll take a few numerical example from this binding energy related problem. We'll take in the next class, and we'll discuss little bit about radioactivity. Okay, in the next class we'll meet again on Wednesday. That day we'll discuss about nuclear forces and radioactivity. Okay, okay, bye for today. Deepa, if you have any question you can now ask me.
No.
Okay, okay, if you don't have any question, then I'll stop it here. This concept will be again clear when we discuss the numerical problems or various questions related to these concepts. Okay, okay then, okay, bye for today.